And our next speaker is Ken Sakayori, who's going to tell us about circuit description languages and some related topics.
Okay. I'm Ken Sakayori from the University of Tokyo, and this is a joint work with Andrea Colledan, Lago from the University of Bologna. And one of the main topics of today's talk is circuit description language. So let me start by explaining this. This is a program written in a circuit description language called Quipper. You do not need to understand what is written here. What you need to know is that a circuit description language is a programming language to describe circuits, as the name suggests. So this program generates a quantum circuit. In this case, this is a circuit that implements quantum Fourier transformation for 3 qubits. Circuits are also low-level programs and hence are meant to be executed on an architecture, in this case, a quantum architecture. In fact, circuit description languages, especially Quipper, do not describe a single circuit. Rather, it describes a family of circuits. In this example, we have a parameter n, which can be thought of as an input to the program. In this case, n represents the number of input qubits. So if n is 3, we get the circuit we just saw. If we change n to 5, then we get this circuit. If we change n to 10, then we get this circuit, which is probably too small to see. And a big circuit may not be executable on quantum architectures. It is well known that quantum architectures still offer limited resources. So, 10 qubits should be okay, but if we make n bigger, there will be a cutting point where the circuit gets too big. By big, it could be in terms of the number of qubits executed at the same time, or it could be the number of gates, or it could be the number of the depth and things like that. So it would be nice to have a way to statically estimate the size of the circuit, and this is what I mean by resource analysis. And meta theory of Quipper has been actively studied in the recent years by studying core languages of Quipper, the Proto-Quipper family. Using these Proto-Quipper calculi, advanced language features such as dynamic lifting, dependent types, or resource analysis I just explained have been studied. The denotational semantics of these languages have also been an active area of research. Actually, if you have a very, very good eyesight, you may notice that there are some overlaps in the references, which I'll highlight for you. So this means that advanced language features such as dynamic lifting or dependent type also come with a denotational investigation. However, the calculi used to study resource analysis do not have a denotational semantics. And by the way, these papers are by my co-authors, and thus I have the freedom to criticize them. Anyway, the motivation of our work and what we did was to give a denotational semantics to these works about resource analysis. So, this is the outline of the talk. The title of our paper is On Circuit Description Languages, Index Monads, and Resource Analysis. I already talked about circuit description languages, so the remaining 2 things that I need to talk about are monads and resource analysis. Let me talk about why we want a monadic semantics and how we achieve that. As we said, a program represents a family of circuits. To match our mental model, the mathematical interpretation of a program should thus be a family of circuits. This property is sometimes called the constructive property of the semantics. And for example, if we have this term in context M, this will be interpreted as a function from the set of natural numbers to the set of circuits. Actually, the set of circuits with 1 input qubit wire and 2 output qubit wires. So this is a family of circuits indexed by natural numbers. And this constructive property is true in existing models for this specific example. One thing I want to note is that, in a sense, this is a closed program. The free variables n and x are the input parameter and the input interface of the circuit, which need to exist. And apart from these, we do not have any free variables. So it would be nice if we have a similar property for arbitrary judgments, or in other words, for open terms. So we want the interpretation of M to be, well, something like this, which is a bit complicated. So that is a function from input parameters to a set of pairs of values and circuits. So if the return value is a unit value, then it means that we have a family of circuits. For now, you can ignore the flat and the sharp symbol. Like in the previous slide, some variables in the type environment is used as parameters or as the interface of the circuit. So we're just using this notation to express this. In short, what we want to do is to separate values and circuits. It would be even nicer if this is formulated as a monad, which represents a circuit generation monad. The reason is because circuit generation can be seen as an effect, and monads are commonly used to represent effect. However, this is not the case for existing models. That is, you cannot separate value and circuits. Let me show you an example to explain this. So let's look at the simplest model of the Proto-Quipper M. Proto-Quipper M is actually one of the simplest calculi among the Proto-Quipper families. So in a sense, this is the simplest model for the simplest calculus. Please don't go away just by looking at this diagram. I will explain the intuition in the next few slides. However, for semanticists, let me just briefly explain this model. So this model is a pre-sheaf model. And the category of circuits, M, which is just a symmetric monoidal category, is embedded into the pre-sheaf category using the Yoneda embedding. And then you get a linear-nonlinear junction. So in short, it is a model of linear lambda calculus with the exponential modality, in which circuits can also be described. And this is the base model of the other Proto-Quipper languages with more advanced features. So in other words, most of the models are pre-sheaf models. Let me explain what I just said in a more intuitive way for those that are not familiar with pre-sheaf semantics. Intuitively, a pre-sheaf represents a family of sets of open values. Parameterization is important to deal with functions that captures free variables because the captured type has a semantic significance. For example, we have two functions here. They both have type unit to int, so they are suncs. The first one captures one label L. Here, label is a pointer to the wire of the underlying circuit. And once the sunc is forced, the underlying circuit is concatenated with gate 1. The second one captures two labels. And once this sunc is forced, the underlying circuit is concatenated with gate 2. So diagrammatically, the two gates that these suncs generate are like this. Note that they have different interfaces. The first one is a circuit with one input wire. The other one is a circuit with two input wires. So what this suggests is that the type of the captured variables, written as the orange subscripts, change the semantics of generated circuits. And very roughly speaking, pre-sheaf semantics allow us to hide this information by considering all the possible cases. So now I can explain why constructive property does not hold for general terms in context. For example, if we were given a judgment like this, we can't tell the shape of the circuit generated by this term unless the type of variables captured by f are given. So this is not a defect per se, but this is an obstacle for compositional reasoning on resources. This is because we don't want to reason about cost functions that takes like wire types and returns the actual cost. Because if this kind of reasoning is too hard for like SMT solvers if we have automation in mind. And the more high order it gets, the more complicated it becomes. And even for humans, it might be quite complicated. So our solution against this problem on the syntactic side is very, very simple. We just allow closure types. So if the types of free variables are the information we need, I mean, why don't we just make that explicit? A similar tweak is actually made in the previous works about the resource analysis for Proto-Quipper. Although I would say that in their work, it is not crystal clear that this is one of the key ideas, partly because this t is abstracted into integers in their work. Of course, this closure type is more intentional. It exposes more information than the usual arrow type A, arrow B. But in the previous studies, my co-authors did some case studies, and with those case studies, well, this didn't seem to be a big issue. So now that we have a closure type, since this talk is about semantics, we need to give an interpretation against it. And the interpretation follows how closures are usually implemented. That is, as a pair of code, I mean a function without free variables and an environment as shown in the first line of the equation. So the s has now moved into the argument part. And actually, the arrow in the first line is the Kleisli exponential. And if we unfold it, we see a monad on the second line. And if we further unfold it, we see the set of circuits. And here, Tm is an indexed, also known as parameterized monad for circuit. This is a multi-sorted version of a writer monad, known as category action monad. And Tm takes parameter Tu, which corresponds to input and output type of a circuit. So, for example, the return is simply an operation that adds an identity circuit, and bind is just an operation that concatenates the two circuits. Okay, so since the interpretation of judgment basically follows that of the arrow type, in our semantics, every judgment does separate value and circuits. So we have what I call the desired interpretation. Then you may ask, is the closure type the only tweak? Well, my answer is yes. And let me quickly show how the language, let me quickly show what the language we consider looks like and the overall semantical model is. Well, what I call in the simply typed case. So this is a language we considered called Proto-Quipper C. So C stands for closure. Its syntax is just the same as Proto-Quipper M, but in a fine-grained code by value style. Recall that Proto-Quipper M is one of the simplest Proto-Quipper calculi. So we have the usual construct for the fine-grained code by value lambda calculus, such as pairs and lambda abstraction, let, and application, and so on. And we also have constructs that are specific to circuit description languages, such as box and apply. However, the syntax is not that important to understand this talk. If you are interested, please see our paper, but the message I wanted to convey is that we haven't modified the syntax. What is more important are types. So there are three categories of types. The first one is wire types or bundle types, which is a type for labels or the wires, such as bit and qubit, or their products, and these are linear. Parameter types are the classical types or the copyable types, which consist of things like the circuit type, natural number type, or closure type that actually captures no linear variable, which is indicated by the I. And types are just either wire type, parameter type, or their product, or the closure type. And once again, what I would like to mention is that the closure type is the only essential difference compared to Proto-Quipper M. One interesting and important consequence of the introduction of the closure type is that every type A can now be decomposed as a pair of parameter type and a wire type. So we write flat A for the parameter part of the type and the sharp A for the wire part of the type A. So these are the symbols that I used in the beginning of this talk. And for example, if we have closure type, if we take the flat, it just returns the type for the code part. If we take the sharp, it just returns T. And if we take the sharp of a product, it just takes the product of the sharp part of each component. And so, as I said, every type decomposes into wire part and parameter part, and this really simplifies the semantics. Here is the overview of our semantic model. It is an instance of parameterized closed Frege category. So what I'm saying is essentially the same thing as saying that we are using index monads to interpret terms. I like to present this in this way because this formalization has a better match with fine-grained code by value syntax, telling where values live. In our semantics, value is considered as a pair of parameter value and the identity circuit, which are the morphism of the discrete category on the left top part. And this presentation also highlights that types are decomposed. Here you can see the Cartesian product of the category of sets and circuits on the left bottom. So it really shows that every type needs to be decomposed into a parameter part and a wire part. Okay, now I would like to move on to the remaining keyword, that is resource analysis. The move from Proto-Quipper C to Proto-Quipper RA, which is a Proto-Quipper variant that is used for resource analysis, is quite easy. The only differences are in the type system, and we simply need to add effect annotations to the typing judgments as in standard type and effect system. So these annotations represent the resource or the cost used by circuit generated when evaluating M. So one thing that I would like to note is that this makes sense because every judgment produces a value in the circuit right now. And also another thing to note is that effects also have the notion of type, T arrow U. This is because effects are abstractions of circuits which are multi-sorted in a sense. And as usual, arrow type also have effect annotations, and similarly circuit types also have effect annotations. So let me explain the intuitive reading of the judgment. The judgment means that the circuit generated by M uses resources at most E. And intuitively, from a semantic viewpoint, we just have this refinement that is giving an upper bound to the set of the circuit. And well, so I didn't say this in the previous slide, but we assume that there is a pre-order between annotations, which is quite standard, I would say. Then the next natural question is, what are the annotations? So we take a very liberal view on this. Our view is that effect annotations are just interpretation of circuits given by a monoidal functor. Well, technically, we consider premonoidal functor in our paper, but I will stick with monoidal functor in this talk. And this means that effect annotations come equipped with the notion of identity and operators for sequential composition and parallel composition. And these operations are used in the typing rules of type and effect system. So the simplest example, well, maybe not the simplest, but one simple example of the effect annotation is that of width. So to count width, we use a category whose morphism and objects are both natural numbers. The morphism part represents the estimated width, and the domain and the codomain represent the number of input and output wires, respectively. For example, the left circuit is abstracted as 2 from 1 to 2 because it has 1 input wire and 2 output wires. The circuit on the right is abstracted as 2 from 2 to 2. For width, the sequential composition is given by the max operation. If we sequentially concatenate the two circuits we just had, its abstraction, or the estimated width, is computed by taking the max. So the estimated width we get is 2, as expected. On the other hand, for parallel composition, we use addition. So in this case, if the two circuits are parallelly composed, then the estimated width becomes 2 plus 2 equal 4. The examples of effect annotations we considered in the paper are gate counts, widths, depths, and gate count after assertion-based optimization that is described in the paper by Hayner et al. So the first two are expressed as natural numbers. The depth is described using matrices over tropical semiring. The last one is represented as a simple predicate transformer. So please have a look at the paper for details. So, and this is a subjective opinion, but we think that the abstraction did help in considering concrete examples. One thing that I would like to note is while width and depth, and also gate count, were considered in the paper presented at last year's POPL', they were treated in a different manner. And now, depth and width are treated uniformly. So now let's come back to the semantics. Is there a methodology to handle these kind of effect annotations? Well, there already is. There is a thing called category graded monad. So rather than indexing a monad with input and output types, we index them with a morphism E. This is a multi-sorted generalization of graded monad. So when we bind two computations, the annotation also gets composed using the sequential composition of morphisms. Okay? And note that for our semantics, we're just using one very specific category-graded monad that gives an upper bound to the set of circuits. And in this case, the monodal structure also lifts. So if you have two computations and if you parallelly compose them, then the annotation is also parallelly composed. And so how do we modify the interpretation to deal with effect annotations? Well, we simply replace index monads with category-graded monads for circuits. So one thing I would like to note is that the interpretation is given independent of the choice of effect annotations. And what I want to emphasize is that our interpretation, after all, follows a very common story. So namely, effects are grades. I mean, in this case, it's category graded, but the moral is the same. And actually, this resembles the construction of a graded monad using effect observations. So this is a general recipe, and we're just using a very specific kind of thing. So the last thing I want to mention are the correctness results for semantics. We have the standard soundness. So I haven't talked about the operational semantics, but there's a big step reduction semantics for configurations. The first one is a circuit. The second one is the actual terms that you're running. And it just says that if you evaluate them and get a new configuration dv, then their interpretation are the same. We also have the standard adequacy. So if we have a configuration that has base type, and if they evaluate to a value, then the interpretation should be the same. And moreover, there must exist a circuit E, which is a circuit generated by the term M, such that the size of E is smaller than the effect annotation, which is small e. Okay, so I would like to conclude. So we showed that the variant of Proto-Quipper used for resource estimation can be interpreted using variants of monads. And the key tweak, or the only tweak we made, was on the arrow type. And the resulting semantics is quite different from pre-sheaf models for Proto-Quipper. And I will say our semantics follows a common story, which is effects are monads and effect annotations are grade. So at the future work, I would like to give the semantics for the full Proto-Quipper RA, which actually has dependent types and effects. So I actually lied in this talk. So when I said this is Proto-Quipper RA, I was considering a variant of it which doesn't have dependent types. So in order to do this, we need to combine dependency with grading. And I actually don't know how to do that right now. And we would like to incorporate more resources or cost to the tool Cura, which is the tool that was presented in the last year's POPL, which can deal with widths and depths. But currently, it is the metrics that we can use is really tied to natural numbers. So we want to generalize that. OK, that's all. And thank you for listening.
Thank you so much. We have time for a question or two. Yeah. Here.
Are there cases where you can't work out the resource cost of the sort of resulting circuit of a program?
Sorry, could you repeat?
Are there programs for which you cannot figure out what the sort of resulting resource cost of your resulting circuit is without sort of running the whole thing through to the end?
Yeah, of course, if the things like the optimization is too complicated, like NP hard kind of things, then we cannot compositionally really calculate. Or if we can do that, it will give a very bad upper bound, so it might be useless.
Sorry, you talk about how this is has a different kind of categorical model than Proto-Quipper M. Mm-hmm. You reuse the sharps and the flats. Am I supposed to interpret them in the same way as the kind of up and down shift, or is it a different notation completely?
I don't think it is related to up and down shift. Yeah.
Any questions? I'm curious as to, I mean, you talk about you don't necessarily know how to combine dependent types with grading. What about some of the other extensions to Proto-Quipper?
Oh, you mean like dynamic lifting and things like that?
Yeah.
I think that is possible, like following the works that were like carried out by like Salinger and their groups. And I think, so it's just an orthogonal relation. So combining the idea, well, I don't really want to say some things that I cannot promise, but yeah, I think that is possible, yeah.
All right. Well, let's thank our speaker again.